It is time to learn about conservative and non-conservative forces, and then this new formula, the work done by non-conservative forces equals change in kinetic energy plus change in potential energy. So let's go for it. Conservative forces. A conservative force takes an object from point A to point B back to point A and does no work on the object. That's what characterizes a conservative force. A conservative force does zero work on an object in taking it from point A to point B back to point A. That's a conservative force. Let me show you an example of this using, and I'll come right back there, using gravity. So imagine I have an object and I throw this object in the air. So this object goes from point A to point B back to point A. As this object is going from point A to point B, what kind of work is gravity doing as this object moves from point A to point B? Positive or negative? Good, negative work. And then this object gets to point B and starts falling. And as it goes from point B to point A, what kind of work is gravity doing now? Positive work. And I hope you see that just mathematically, the negative work it does in taking the object from point A to point B is going to be equal but opposite to the positive work that gravity does in going from point B to point A. You see that? So gravity does no work in taking an object from point A to point B back to point A. That makes gravity a conservative force. Conservative forces. Gravity. Let's consider another force. Here, I'll walk back over there. Spring force. Here's my mass. My mass is on the spring. And my mass, maybe it's bouncing up and down, oscillating, whatever. But let's say my mass goes from point A to point B back to point A. Well, consider the force that the spring is exerting on the mass. As my mass goes from point A to point B, as the mass is compressing the spring, what kind of work is the spring doing, positive or negative? Negative, I hope you see, because as the mass is going down, the mass is moving that way, but the force of the spring is upward, because the spring is compressed right now, so it's exerting a force up. So the spring does negative work on this mass as it goes from point A to point B. Then as the mass goes from point B to point A, what kind of work is the spring doing? Positive, right? Because now the spring is still exerting a force upward. In fact, the spring is what's pushing the mass up, and the spring is moving up. The mass is moving up. So I hope you see that the spring is doing zero work in taking the object from point A to point B back to point A. This can also be seen pretty clearly if we consider a spring that only stretches but doesn't compress and stretch, right? Here, look at this. As this mass goes up and down, let's consider the point A as being the mass's equilibrium point and point B being lower than that, right? I want you to see that as my mass goes down, okay, point A is equilibrium. As my mass is going down, the spring is pulling up, correct? So that's negative work. Then as the mass comes back up, the spring is still pulling up, but now the mass is moving up, so that's positive work. So you end up getting zero work done from point A to point B back to point A, and then when the mass rises up and comes down, zero work is being done as well. So the spring is a conservative force. But let's consider some non-conservative forces. Here, let's consider kinetic friction, okay? This mass is going to move from point A to point B back to point A, and we're going to consider what kinetic friction is doing to this mass. As I go from point A to point B, tell me, what kind of work is kinetic friction doing? Positive or negative? Good, negative, because the friction is opposing its motion, right? Friction force is acting that way as the mass moves that way. Now I'm going to move this mass from point B back to point A. What kind of work did kinetic friction do now? Negative again. In fact, kinetic friction only does negative work. Same with air resistance. Well, not really, but we'll just pretend. You can have a situation where air resistance does positive, but then it's not air resistance. It's like the wind blowing on a sail or something. But as far as friction goes, or resistive forces go, those are non-conservative forces. You could never get zero work due to friction, because friction's always doing negative work. There's no positive to ever balance it. Let me show you another force, normal force. I'm going to push on this eraser. I'm going to push that way and move the eraser that way. So what kind of work is normal force doing? Positive work, correct? And now I'm going to make this mass go back from point B back to point A. I'm going to exert normal force. See, I can't do it from this side. I'm going to have to do it from this side. And if I'm exerting normal force on this side, pushing that way, what kind of work is normal force doing now? Positive again. You see, normal force, I can't take an object from point A to point B back to point A with normal force and have it be zero work. Because your normal force is always doing positive work. Your normal force is always in the direction of motion of movement, or direction of the movement. So a normal force is a conservative force. And as you're going to see in a moment, the same thing happens with tension. Here's tension on my yo-yo, correct? My tension is moving the yo-yo from left to right. Tell me, what kind of work is tension doing? Positive work. And now I'm going to try to move the yo-yo back, and I can't do it from here. I've got to do this, and now I'm doing more positive work to get the yo-yo back to point A. It's not like the way gravity or spring force worked. So tension is also a non-conservative force. Great. So those are your non-conservative forces, those are your conservative forces. Now I'm embarrassed to say, and I say this because this is being videotaped, this is the high school version of this stuff. Actually, particularly according to Richard Feynman, the Nobel Prize winning physicist, there's actually no such thing as non-conservative forces. Because your four basic forces, gravity, electromagnetic force, strong force, and weak force, those are all conservative forces, and that's all we've got. So this is kind of a construct we do in high school to make this distinction, but actually, friction force, normal force, and tension, those are all electromagnetic forces. Those are intermolecular forces, which are electromagnetic in nature. So just between you and me, there's no such thing as non-conservative forces. But we do this in high school just because that's what we do. So there it is. Here we go. So now you got it? Those are the non-conservative forces right there. Great. So now we're going to learn about this beautiful formula here. I want to remind you that what I taught you yesterday was work is defined as what you have to do to an object to change its energy. Work is equal to change of energy. And so we learned another type of work. We learned that net work on an object equals the change in kinetic energy. But now that net work is going to be a combination of work done by conservative and non-conservative forces, right? So I'm going to let W sub C equal work done by conservative forces. Work done by conservative forces. And I'm going to let W sub NC be the work done by non-conservative forces. And that's all I've got. There's no third option besides conservative forces and non-conservative forces. So this ends up being the work done by the conservative forces plus the work done by the non-conservative forces equals the change in kinetic energy. You guys okay with that? The net work has to be the sum of these two works, and that's all there is. Well, when it comes to work done by conservative forces, so far in our little high school class, all we've learned about is gravity, right? So I can actually get an expression for the work done by conservative forces. I can get an expression for the work done by gravity. I'll just go back to this drawing where this mass at an initial height of h naught falls to a final height of h sub f, correct? And the work gravity does is the weight of this object multiplied by the distance it travels. So the non-conservative work is going to be mg h naught minus h sub f plus the work done by non-conservative forces equals change in kinetic energy. And now I'm going to put this, I'm going to distribute this and put this on the other side of the equation. So I get the work done by non-conservative forces equals change in kinetic energy plus mg h sub f minus mg h naught. And what do you suppose I'm going to call this? Yeah, change in potential energy, right? That's the final potential energy, that's the initial potential energy. So this ends up being change in potential energy. And that's our happy little equation. The work done by non-conservative forces equals the change in kinetic energy plus the change in potential energy. As we learn about more potential energies, as we learn about spring potential energy and electrical potential energy, that just adds more items right here on our equation. Then I'll end up with the work by non-conservative forces equals change in kinetic energy plus change in gravitational potential energy plus change in spring potential energy plus change in electrical potential energy. But for now, all we know is gravitational potential energy. There's one more thing I want to tell you about this before we go on. We're going to learn that only conservative forces get to even have potential energies associated with them. There's gravitational potential energy. We'll learn that there's spring potential energy. We'll learn about electrical potential energy. But there's no such thing as friction potential energy, normal force potential energy, or tension, potential energy. And like when we learn about buoyant force, there's no such thing as buoyant force potential energy. All the non-conservative forces don't have potential energies associated with them. Only the conservative forces. All right, hey guys, well that was fun. It is now time for us to do problems. I'm going to show you an example. I'm going to have you guys do an example, then I'll declare us done. Here comes example number 1. You're on a roller coaster. Okay? Your initial velocity is 0. Your roller coaster is 58 meters above the ground. The mass of this roller coaster plus the human being inside of it is 150 kilograms. This roller coaster is going to go down this hill until it ends up right here. And at this point, the roller coaster is going a speed of, and let me refer to my notes because I'm actually getting this off my notes. Obtains a speed of 32 meters per second. That's the final velocity. And I'm going to ask for how much work do the resistive forces do? That is friction and air resistance. What's the total amount of work done by friction and air resistance? Find the work done by friction and air resistance. Your clue that you're going to have to do a problem like this is that they, I'm not sure they gave you enough, well, I guess they gave you enough information to do all that F equals MA stuff, but not really, and it'd be a real big hassle. But they sure gave me the initial kinetic energy and the initial gravitational potential energy and the final kinetic energy and the final gravitational potential energy, and they're specifically asking for this. They're asking for the work done by non-conservative forces. Sight unseen, if they ask you for what is the work done by the non-conservative force, definitely you're going to consider using that formula. So here it comes. Let's do it. Work by non-conservative force equals change in kinetic energy plus change in potential energy. Okay? The work done by non-conservative forces equals. You have to make sure you have it really clear in your head what the initial and final scenarios are, what the initial and final position is. Are you guys okay that this here is the initial position? So any kinetic energy or potential energy that you're calculating are going to be for this guy here. This guy here is in its final position. So let's go for it. This is going to be 1/2 mvf squared minus 1/2 mv naught squared plus mgh sub f minus mgh naught. Now let's plug in my 1/2 times 150 times the final velocity is going to be 32 minus, what's my initial kinetic energy? You guys getting 0? Do I have to put 1/2 times 150 times 0, or can I just put 0? Okay. What's my final gravitational potential energy? Well, the beautiful thing about gravitational potential energy is you can define any arbitrary point as 0 gravitational potential energy. So why not just define this guy as 0? That is, define his final position as 0. So that the initial position, he's going to be 58 meters above that. So I hope you guys are getting that the final gravitational potential energy is 0. And I got minus 150 times 9.8 times, what is that, 58? And now I just solve. So I got 2 seconds. I'm getting negative 8,460. All right. Which for 2 sig figs will be about 8,500, negative 8,500. Does it make sense that the work would be negative? Why? Why does that make sense? Someone just tell the class. Yes? Good. Why do they do negative work? Thank you. Or not the opposite direction of acceleration, but the opposite direction of its motion, of its velocity. Yeah. Friction and air resistance always oppose your velocity. So they're doing negative work. If I had gotten a positive, I have to confess, I did a bad punchy last period, and I ended up with a positive answer here. And I knew immediately I had it wrong, because I knew friction and air resistance have to do negative work. And I got like positive 16,000 or something, and I went, oops. And it turns out I hit the division button instead of the multiplication button for one of them. Okay. Hey, you guys ready to do it on your own? Of course. Good. Thank you very much. All I needed was one correct answer, one affirmative answer. Here it comes. You got a toy rocket. Example number 2. The mass of this toy rocket is 0.20 kilograms. Okay. Starts at rest on the ground. The fuel does 425 joules of work. Remember how fuel how fuel works? The rocket pushes down on the fuel, so the fuel pushes back up on the rocket. So it's essentially the fuel is like a giant hand pushing the rocket upward. So the fuel does 425 joules of work on the rocket. And it gets to 29 meters above the ground. Find its velocity at that point. Good luck, you guys. Good luck. And Leilani and I will walk around and help you. Oh, I never said that it was, oh, okay, I said it's a rocket. Here, I'll make it. Make my rocket. If anyone's having trouble where to start, please make sure you do work by non-conservative forces equals change in kinetic energy plus change in potential energy. Good luck. There's your initial position, there's your final position. We're not going to walk around and help. Same with you, Chris. I see a correct answer. Let's see what we got here. Good for you. Alright, so that should be positive, isn't it? Yeah, your final gravitational potential energy. Okay, cool. Oh, that should be a 29.
Oh.
But you did it fine. If you want to get a right answer, but you did it right. And that's all I care. Yeah, looking good.
Oh.
Yeah, because it's at the ground. It starts on the ground. Oh, we're so smart, aren't we? We're so in love with ourselves. Yeah, that's correct. So you're very smart. Don't ever change. Some of you don't ever change. No matter what anyone says.
I've lost. Yes, that's great.
All right, yeah, hey, so far so good. Let's see what we got here with section. Wait, just 1 second. Now that guy shouldn't be negative, like both of these guys should be positive, because the only things that have values are the final values. Like both initial values are 0. Okay, cool. All right. So, and did you put, oh, you got to put 425 on the left side. I give you the non-conservative work, it's 425. Good. Oh, can I interrupt you? The final kinetic energy isn't 0, it's the initial kinetic energy that's 0. That's the non-conservative work, so that goes on the left side. Yes, you can, especially because you got that correct. Oh, did you guys win last Friday? Oh, I mean, how bad was it?
48-7.
Okay, that's about right. You know, comparable teams against Rancho and Upland, that's about the score they lose by. Good for you. Yeah. Oh, what's the answer? 60.7. What was I looking at? Oh yeah, you're doing right. Are both of your terms positive? Because, yeah, see, this is the second one, right? But you'll notice the initial value, the initial speed and the initial height are both 0. So like this guy and this guy should both be 0. You should have both of these guys being positive. You have a final kinetic energy and you have a final potential energy. You see, both the initials are 0. Yes? Sure. Good. Yes. Good for you. The smart part of the class right here. All right, everyone get it. What'd you get?
Why does it work? Gravitational potential.
Let's see what you got. Yeah, both your terms are positive for the initial terms of
I'm just like numbers, to be honest.
You get it right? What you mean? Oh, remember, work by non-conservative forces is. That's it. That's the non-conservative work technique. You're welcome. All right, happy students.
You can only use part more. Yeah, I mean, it's easy for you, I guess.
If you want to say that,
That's her point all the time.
I think I never.
Yeah, you can just say that.
The other day, get great.
Well, there's no conservative forces that are going to, no conservative work on the left side, because all the conservative work is going to be taken care of by the potential energy term on the right side. Is that what you're asking?
Yes. Yes.
Okay, yeah, so the only work that'll be on the left side is work done by tension, friction, or normal force.
He was asking mainly like how do you find the change of kinetic energy, and he wanted to know if you use potential energy, right? Is that what you're asking?
No, I was like, for the formula work, like force. Okay. Distance.
Yes.
Is this, does that include both conservative and non-conservative?
Yes, if you're going to use that, then it has to be net force, and then you're considering all the forces. Yes. Yes.
Did I just like punch like
Love people though.
I know it.
Would you do something else? Last night I was doing my UC, you know the UC for English. I couldn't think of anything to write down. So I sat there. I started at 8. Girl, are you not I do, but like I don't know how to like and also so I stayed until 2 doing it. Like you're just right. It was just rough draft. That's what I was thinking. The last one that I did, I'm just filling up paper.
Because what I did is I spent a lot of time with just like 4 really good ideas for questions. But then like, I was doing the rough draft, I put as much ideas down.
Is there any question or problem on this answer, 60.7? Anything you want to talk about? Anyone get it wrong, not know why they got it wrong? I mean, Leilani and I walked a long round and it looked like pretty much everyone was getting it right. And that's good. Okay, then, hey, it is now time for me to pass back your exams and talk about the exams. So we can turn this baby off. Bye-bye.